All right, so for today we are learning about linear programming, which is a fairly large process. And you have a sheet with this problem written on it. And the first thing to notice is that there isn't a single thing we can do in order to solve this. We actually have to go and look at this in more depth. Because it's not like I can just write two equations and solve the system of equations. There's more to it. So, on that sheet, I gave you those boxes there to complete. We're going to fill those in first. And we're going to fill them in using the information that's here in the written problem. So first thing I want to do is down the left-hand side, I'm going to label the two things that this problem is really about. So as you take a look at this problem, it's giving all sorts of numbers and all sorts of information, but it's all having to deal with what two things? The tomato plants, right? The two types of tomato plants. We have both Roma and cherry tomato plants. So I'm going to label Roma down the left and cherry down the left. All right, and now I'm going to look through that problem and start looking for, okay, what's it tell me about those? And one of the things that jumps out to me right away is I see some money involved. I see this $40, this $2, and there it is, this $3. And we want to know, well, those all have to do with some sort of a cost. Specifically, the 2 and the 3, those are a price per plant. And so above my next column in that little table I gave you, that's what I'm going to write. Price per plant. And I know that the price per plant for each Roma cost $2. So I'm going to go ahead and put that $2 in there. And each cherry plant, that one costs $3 each, so I'm going to put the $3 in that box. So notice as I look down in this table of information, I can see that the price per Roma is 2, the price per cherry is 3. But there's another number given that has to do with money. We also have this 40 here. Now that 40, it's a limit. It can cost no more than $40. So at the bottom of this, then, I'm going to put the $40. Now, in this case, it says we can spend no more than 40. Does that mean we can spend less than 40 or more than 40? Less than. We can spend less than it, but not more. So I'm going to write a less than or equal to sign in front of that $40. And the beautiful thing about making this table is it's then going to allow us to just look at this table of information when we're all done with it and pull together everything we need. We're not going to have to keep going back to this paragraph every time. We just use it to pull everything into the table and we're going to be done. All right, so next up, what other information are we given? Well, we're also told about how much we get out of each plant. So like I got this 10 pounds per plant here, and I have this 8 pounds per plant down here. Well, that's how much each plant produces. Now I'm going to get a little fancy on you here. The amount that something produces is generally called its yield. So I'm going to title that column yield. But as you're making it for yourself, you might have called it amount produced or something like that. I mean, it's the same thing. All right. So now for the yield. How much do I get per Roma? Look down at the paragraph. How much is the yield per Roma? 8. Yep. It is 8, and I'm going to be specific here, is 8 pounds per plant. And how much is it per cherry? 10. And I'm getting that from the paragraph down here. So that's 10 pounds per plant. All right. Now, in the last one, when we were dealing with the money, the price per plant, we were told that we could only spend $40. Is there some sort of a limit on the yield that we want here? Does it say we have to make at least a certain amount or at most a certain amount? No, there's nothing about that in there. What it does tell us, though, is we want to maximize his yield. And so I'm just going to make a little note at the bottom of that column that I want to find the maximum of that. I want to maximize those numbers. All right, now we got one more column in this pre-done table for you. So what haven't we used yet? As you look down that paragraph, we're looking for anything that we haven't used yet. What haven't we used? Yeah, we haven't used that 15. We're told that he can plant at most 15 plants. Okay, so then I want to label this column number of plants. I'm going to be a little bit more specific. I'm going to say total plants here. And now sometimes this can bend people's brain just a little bit. How many plants do we get per Roma? 1, right? And how many plants per cherry plant? Just 1. Yeah, sometimes that can be a little bit weird because we're just looking at the total plants needing to be less than or equal to 15. So oftentimes I'll just write it like that, where I just say it's total plants and I don't write anything in the box. But you can write in the box if you do want to put those numbers in. Each Roma is 1 plant and each cherry is 1 plant. All right, having made the table, we're now done with the paragraph. I took every piece of information that was in that paragraph and I put it into this table. So now I don't even need to look back at it. That makes our lives a whole lot easier, because if we are continually going back to that paragraph, trying to find the information I need at this particular moment, we'd spend all our time hunting through all the words. Now I'm just using that paragraph. Now in the paper I gave you, you notice you have some sections already labeled for you. One of them is variables. That's because the first step in doing one of these problems is to identify the variables. Now, what are my 2 variables in this problem? Notice what I said there. 2 variables. There's always exactly 2 variables in a linear programming problem. That actually helps you know what they are, because where do we see just 2 things along the outside of our table? The tomatoes. Now, we're going to be writing some equations, some inequalities that deal with these things, and so I don't really want to use x and y. Technically, we can use x and y, but if we do so, it's going to be kind of hard to remember which one was Roma and which one was cherry. And so instead of using x and y for each one, I'm going to use something that means something. I'm going to use R for the Roma tomatoes, and I'm going to use C for the cherry tomatoes. Please write down those definitions under your variables section on your paper. And then the next section that you have set aside on your paper is called constraints. Now, constraint, that's just a big fancy word that just means like a limit. Something that says we got to be above this or below this. Notice we have 2 of those, right? There are 2 constraints in this particular problem. Now, sometimes you'll see more than 2 constraints. We will always have 2 variables. And you might want to make note to yourself if you want to on this problem so that you remember there's always 2 variables. For the constraints, there can be 2 or more constraints. And you're very quickly going to be seeing problems that have 3 constraints and even some that have 4 or maybe even 5 constraints. But we can have many of them. Now the constraints are the limitations. And so if we take a look up at our table, we can see that we have 2 constraints. 2 of them that have a greater than or a less than symbol in them. And that's what tells me I have a constraint. So first one, price per plant. So I'm going to write a constraint for that price per plant. This is where the table is a beautiful structure. The table technically is just a structure I'm giving you to organize your thoughts. It's strictly not required, but boy does it help at this point, because my first constraint can be $2 per Roma plus $3 per cherry, having to be less than or equal to 40. Look at that. I just went down the table to write that constraint. That's our first constraint. Another note that you can make about constraints is constraints are always inequalities. That is, they're the greater thans and they're the less thans. All right, so we did that constraint. Our other constraint comes from this less than or equal to 15. Well, remember, if we wanted to, we could include the ones in there on the number of total plants. So that'd be like a 1R, well, 1R is just R, plus like 1C, of course that's just C, has to be less than or equal to 15. And so if I want to know the total plants, I take the number of Roma plus the number of cherry, and I set it less than or equal to 15. All right, so this is where we're at so far. Notice again, I'm using R and C instead of X and Y because when I go to use these again later, I want to know where to plug each one in. And if they're X and Y, it makes it kind of tricky to do. All right. The next section that I have pre-labeled for you is objective. The objective, a few little notes about the objective here. There is always going to be exactly one objective. And our objective is always an equation. It's not an inequality or anything like that. And specifically, our objective is what we're trying to maximize or minimize. And so in this particular problem, hopefully it leaps out to you which one that is, right? Because if I look up at my table, I see that word maximize at the bottom of that column. So I know that my objective is going to have to be the yield. And so how would I calculate the total yield? Well, again, I can just go down that table. Notice it is 8 per Roma. So that means it's 8R. And it's 10 per cherry. Every time I can say per, that means multiply. So 10C. Now, I'm just trying to maximize that. That's how I calculate it. Yield equals that. And so I'm then going to note with that equation that I'm trying to maximize it. Because I want to later remember that I'm trying to find the biggest number out of that. This equation, by the way, is also an illustration about why we are learning this process instead of just like finding these two as an equation and just figuring out where they cross or something like that. Because with the yield in there, we've actually introduced a third variable. And so we're trying to figure out how do these two equations with two variables relate to this equation with 3 variables in it. Now, all of this work that we've done so far is just prep work. This has been preparation for making a graph. So that work that we've been doing the last few days, practicing graphing, now it's going to start coming into play. We're now going to be applying that information and that knowledge. So, if I'm going to make the graph, I now need to figure out where my X and Y intercepts are. The reason is because I'm going to graph the constraints. This is what we graph, only the constraints. Notice the objective does not get graphed. So the objective, not graphed. Why? Because it has 3 variables in it. How can I graph something with 3 variables when I have 2 axes? And so we're going to graph our constraints here. Now, when I graph the constraints then, that means I have standard form inequalities. Standard form, there we go. Standard form inequalities, and so I have to find the x-intercept and the y-intercept, or in this case, the r-intercept and the c-intercept. Now you remember how to do that, right? So like if I want to find the r-intercept for this first equation, I'm going to plug 0 in for c. And so I have 2r is less than or equal to 40. So then that's going to give me 20 for r when c was 0. Now notice I'm writing it as a coordinate pair with r first and c second. It technically could go either way, but as a matter of habit, you always want to keep it in the same order because we're used to seeing whichever one is first as being our x, and so treat it like it's your x. But just realize that technically we could do it either way with these. It's just going to cause some problems for you later if you switch them around, because everything else in this problem is going r then c. So I want to stick with the idea that that's x then y. All right. Now I want to find my Y-intercept, or in this case my C-intercept. And so that means plugging 0 in for R. Well, now I have 3C equals 40. What's 40 divided by 3?
13.3.
Yeah, it's 13 1/3 or 13.3 repeating. Yes, it's a decimal. Yes, we're going to deal with it anyway. We're just going to estimate where it is when we go to plot it on the graph. And then repeat the same process for the second constraint. Obviously, both intercepts there are going to be 15. So I make note of what my intercepts are. And just like on the assignment that we did yesterday, I use those to decide on my scale. Once again, like yesterday's work, I've given you a graphing grid that has 20 boxes in it, each side. So I take a look at the information I've found. So my R-intercept, I got 20 and 15. So that one has to go out to 20. What should we go up by? I need to get out to 20 here. So what am I going up by? 1. Yeah, so you're going up by 1s there. Now notice I just decided that was going to be my R-axis. So label that axis as Roma. And then I need to take a look at the cherry tomato intercepts. Because remember, I'm treating, since I wrote all my C's second, I'm treating that as my Y. Okay, so there I have numbers of 13.3 repeating and 15. Well, I don't really want to put 15 up here because that's going to make me go up by some ugly values. So the nicest one I can go by is, yeah, let's go ahead and make this one 20 as well. So that means, once again, I'm going to go up by 1s. And since I'm labeling that axis, go ahead and also label it as cherry. Label that axis as being the cherry tomato plants. Now I haven't labeled every single hash mark there, going 1, 2, 3, 4 on both axes. I've just put enough where I can make sure that I find accurate numbers without having to do too much counting. You certainly are welcome to put in more hash mark labels. I probably wouldn't put in much less though, because it can make it hard to find the numbers when you're actually counting them, and it can sometimes lead to a count error, which after you've done all the work we end up doing on these, you don't want a silly thing like a counting mistake to throw off your results. And now that we're at this point, our next step is to go ahead and make the graph. Well, we've practiced making these types of graphs recently, so I'll go ahead and let you loose on that. Go ahead and just make the graph of these two constraints. All right, so when you go and make this graph, let's just check, make sure everything's going well. I first do the first constraint, so that's going to be the point 20, 0, and the point 0, 13 1/3. And again, you're just going to estimate about where that 13 1/3 is. And then draw the line that connects those. Use the straight edge though, because if you don't, you're going to notice some problems. All right, for the second one, I'm going to 15, 0 and 0, 15. And again, use the straight edge to connect them. I don't have a straight edge on this, so I'm drawing that in. Now, we shade then. Notice the signs on both of these. Both of these are less thans. So I'm shading both of these below. And so the actual region that gets shaded then is going to be this whole region where it's below both of them. Now, you notice I didn't use a straight edge. Notice it kind of looks like they're crossing there. Notice when I did use a straight edge, where they actually do cross. We're going to need to be able to see where that point is. So that's why being precise matters a lot. And then a few other little details I can give you. First of all, this region that you're shading, we refer to that region as the feasible region. So as we discuss the feasible points in the feasible region, we're talking about that shaded area. The other thing I want to mention is that there's actually a couple invisible constraints here that we didn't actually discuss. Because you notice I started by just giving you quadrant 1 to graph it, just the positives. Technically speaking, we could actually write constraints that say that x must be greater than or equal to 0 and y is greater than or equal to 0. We just often leave them out as actually being technically listed. mostly, honestly, out of a sense of laziness. But they have to both be greater than 0 because we're talking about the number of Roma cherry tomato plants. We can't have negative tomato plants. And so when dealing with these, we're generally just dealing with the positives because we are just looking to see where are they actually possible. And so we're just looking at positives here. All right, now, we did all of this work over here and up here just so we can make the graph. We made that graph just so we can see where the corner points of the feasible region are at. So, all of that work was just done so we can find this point, and this point. Now, those are going to be the ones that we're actually going to see as possibilities. Now, a little bit of detail here before we get too far into it. This point right up here, that was at 13 1/3, right? Specifically, 13 1/3 cherry tomato plants. Can I have 13 1/3 plants?
No.
No. So what point should I actually use there? 13. Could I use 14? Like, what if it was like 13.9? Could I use 14?
Yeah.
No. It might round to 14, but notice 14 wouldn't have been shaded because it has to be below that number. And so since it has to be in that shaded region, you really have to be looking, what's the closest number that is shaded that I can go to? So these are the 3 points that we're actually concerned about. 0, 13, 5, 10, because we used a straight edge, drew it carefully, we can see where they cross there, and 15, 0. Now what if you can't tell where they cross over in here? Well, then you get the joy of taking this as a system of equations and solving that system algebraically to see where they cross. Do you really want to have to do that? No. So make your graph neatly and accurately in the first place, and that won't be an issue. You'll be able to just look at it and tell where they cross. Now, those 3 points are the only 3 I care about. Let's make sure you understand why those are the only 3. Every point that is shaded is a possible, feasible point. So like that point that I just labeled right there. Is it possible that that point would give me the maximum yield? I would say no. Because remember, I'm getting a certain amount out of each type of tomato plant, right? Well, I can go up from that point and get more plants, and each plant gets me more stuff. It gets me more yield. So if I can still go up from that point, that means I can still get more yield than that one point. Same thing if I can still go to the right from that point. I can go to a point that's going to give me a greater yield. So automatically, just based on that, that means that our winning point has to be one of these points along the border. Now, of those points along the border, if it happened to be like one of these points, if one of those gave us the maximum value, it would have to be exactly the same as one of those. Otherwise, if I'm at one of the points on this line, if I move upward or if I move downward, it's going to be changing the value until we get to a corner point. So all of that just to say that when we do one of these problems, we only need to worry then about the corner points of that feasible region. Those are the only possibilities for where our maximum, or in later problems, minimum, could possibly occur. Alright, so once again, we did all that work just to make the graph, and we did the graph just so we could find out where those 3 points were. The reason why I want those 3 points is because I now can take those 3 and plug each one into the objective to see which one of these points is the best point. That is, I'm going to plug those coordinates in for R and C in the objective function. So for instance, in this first one, I'm going to take the point 0, 13, and I'm going to plug that in for R and C. So that means I'm going to do yield. The yield at that point is going to be 8 times 0, because my R value is 0, plus 10 times C. My C value here is 13. And I'm going to see what that equals. And again, notice by making it R and C rather than X and Y, I'm keeping myself from making a mistake here. And so I plug in that point, 0, 13. I plug in the 0 for R, the 13 for C, and I see what that equals, and it gives me 130 for that first yield. Repeat the process now for the other 2 points. See what our yield is for each of those now. And when we've done that, these are the numbers you should be getting. 1 point gives us 130, the other one 140, and the other 120. Now what am I looking for here? Am I looking for the biggest or the smallest number? The biggest, yeah, because remember we were told to maximize. That's why I wrote maximize down there. So we'd remember, hey, I'm looking for the maximum number out of those 3. So that means 140 gave me my highest number. That means that the point 510 that I plugged in to get it is my best point. And so, how do we do this problem? We started with that paragraph, and we turned that paragraph into a table. We then took that table and turned it into variables, constraints, and an objective. Having done that, we then took the constraints and we graphed them, so that we could find each of those intersection points. Also, we could plug them into the objective and find out which one was best. Now, having figured out which one is best, I don't want to just see a whole bunch of numbers with an arrow pointing at it. We actually need to write out our final answer. So for our final answer here, we would say that this farmer should plant 5 Roma and 10 cherry tomato plants for a yield of 140 pounds. This is dealing with a real-world situation, so we're giving a real-world kind of answer. And then, finally, you're done with your first linear programming problem. Yes, all of that was a single problem. And long as it is, it at least gives you some context and idea about why have you been doing a lot of the stuff that we've been doing up to this point, because it's been helping you to get ready and have the skills to be able to do a problem that looks like this.